We'll look at linear regression in this video. So let's say we have a database which tries to map the salinity of oceanic waters vis-a-vis the temperature. We could start with linear regression to explore the relationship. As we always do, we'll quickly start with reading from the CSV file, and then we'll do a basic formatting. Once we do the basic formatting, we will quickly create a fit model using command ln, and I'm going to map the response variable and study the behavior of this response variable against the temperature. So temperature is an independent variable and response variable is a dependent variable. So we do a quick summary and we can see that it has done a y is equal to mx plus c kind of a plot where we have a constant intercept, and the slope here would be as per the variations in the temperature and how those variations affect the response variable. So we can quickly see that the p-value is very less, and both intercept as well as the input variable are significant. That means we know that they have a role to play. Once we do the linear modeling, we can also quickly do a plot. So this helps us explore the relationship between temperature and salinity. And another aspect of this is to understand the residuals. So residuals is the difference between the fitted value, which is arrived at as per a given model. In this case, it is linear regression, and the corresponding response variable y. So it's a difference between y and y hat, where y hat is the fitted value for the response variable. And we need to understand how these residuals are, and we have to also validate our assumptions, because when you're trying to fit a particular response variable as per a given model, we need to check whether the error terms are having constant variance, that they are typically normally distributed, and the error terms should not be dependent on each other, right? So that those are certain fundamental assumptions that we have to validate in order to validate our linear model. And for that, we do something called as a fitted value analysis, and we can extract the fitted values from our model. We store that in variable ln fit, and once we plot that, we can quickly visualize how the residual values look like. And let's begin the analysis of residual variables. We could also choose to normalize the residual values, which basically subtracts the mean from each of the mean of residual values from each of the residual values. So a quick way to visualize is to do a simple plot of fitted values versus the residuals. This allows us to understand how the residual values are distributed across each of the estimated values of the fitted variable y hat, which tries to emulate or estimate the original response variable. So these values are expected to be randomly distributed. They are expected to be symmetrical, so that the mean is expected to be 0. That means the mean of the residual values is expected to be 0. So those are some checks that need to be done. We can also highlight points of interest by choosing a different color mechanism. So I'll just use a quantile function to color only those who belong to the 95th percentile. So typically quantile gives me 4 different percentile. I'm trying to find out which are the points of interest that are between 95 to 100%, right? Those are the points of interest. And so that's one way to visualize that. I can also do a quick skewness computation like we did earlier for those who are interested. So essentially, this positive value of skew hints towards a right skewed distribution of residual values. Similarly, I could do a process computation as well. But we'll quickly jump to doing a quick histogram, which quickly allows us to visualize how the residuals are distributed. For instance, we can see that it seems like a multimodal distribution where I have three different sets of three different bin sizes, right? One is at the center, and then either one at the extreme ends. We know that this is a light tail distribution. Tails are curved at either end. So that's another way to visualize this. Let's move on to do a QQ norm plot. This allows us to understand how the residual values are compared to a normal distribution. Where normal distribution is a straight line, and we can see that it is flattened at either end. That means the tails are curved, and again hints towards the right skewed distribution as it starts from below the normal line and then gradually catches up. So this is what we discussed earlier as well. So another important aspect is to